Hello guys, how are you doing? So today I'm going to start a lecture about rigid body equilibrium in 3D and calculation of the reactions. That's what we're going to be doing today. So let me change this thing so I can put this one. Good. Yeah, last lecture. Before starting with this, I would like to go with what we covered last lecture. So last lecture, basically what we were doing is 2D equilibrium reactions also for rigid body equilibrium. And we said the main three types of support, it's not limited to those, but the main three types of supports that we were using is a roller. And remember always, a roller produces one reaction perpendicular to the wherever the roller is supported or supporting the structure, perpendicular, not vertical, perpendicular to the surface. And then you have a pin. Whenever you have a pin reaction, a pin support, I'm sorry, the pin produces two reactions in any two directions, any two non-collinear directions, because if they are collinear, it's only one direction. And remember, you have UV axis also, and they don't have to be perpendicular. What happens is, for practical purposes, we make them perpendicular because that's where we reference what our reference is supposedly all the time like that. But also you can say that produces only one reaction with a known line of action. What happened with this is, personally, my preference is seeing things like this and not putting them in terms of forces and angles. The difference between this and the roller, in the roller you know the direction of the force, perpendicular to the surface. With the pin you don't know the direction of the force. So what you have to do is then, if you want to convert this in x and y, you're going to say f cosine of the angle and f sine of the angle, but you don't know the angles. So if you're going to have two unknowns, I rather having the two unknowns like that and not like this. So two, let's say x and y for our purposes, and fixed support restrain the movement in the three different directions, the two translations and the one rotation. And if x and y is the plane xy, what contains the forces and the distances, then the moment will be in z direction. You don't have to say it because it's obvious, but apparently it's not that obvious, because I made a question today during my class, and the majority of the people didn't even know that that moment goes in z if the plane is x and y. And then you have to remind them, oh, remember cross product, okay, the only possibility for rotation is about the z direction. Okay. And there are many other type of supports, but then you have this is a roller, it's the same thing, restrained in both directions, perpendicular. This is a roller also in only one direction, weightless link, cable. I always tell my students a weightless link, if you want to imagine it like a cable that can also push, because in the case of the cable, it always produces only one force, that is perpendicular, like parallel to the in the direction of the cable. But in the weightless link, it could be in the tension is only pulling. In the weightless link could be in either direction, either pulling or pushing. And then you have the rocker. I always say the rocker is like the second cousin of the roller. So same with the smooth contacting surface. For all of our purposes, these two are behaving like rollers. One reaction perpendicular to the surface. And then you have also these other type of supports. And more than naming it member pin connected to collar on a smooth rod, I don't know, I have been teaching statics for 30 something years and I still don't know those names, and I don't want to learn those names. So basically you just verify and review what movements or rotations are allowed. So basically, if I can move this in this direction, I can slide it in that direction. The meaning of that is that you don't have any restraining in that direction. Now, if I try to move it in this direction, obviously I can't. That means that I have a reaction in that way. And because this is a pin, I can get this arm and rotating it, or rotate it about the pin, and it's free to rotate, meaning there's no the moment constraint, there's no the moment reaction. So this behaves also like a roller, one force perpendicular to the surface, in this case perpendicular to the sliding plane. Pin, we already discussed that, either 2 or 1. Now this one is the same case like this one, but now we welded we restrain also the movement in this direction. If we restrain that movement, what it means is that basically there is a moment reaction that is being produced there. And fixed support, 3 reactions, 2 forces and 1 moment reaction. That's basically what happens over there. We talk a little bit about free body diagrams, and then we were over free body diagrams, and we said draw the outline shape, and then imagine the body to be isolated, and start substituting all the forces and reactions in the member that you cut out. That's basically what we did. And I went to several examples like this one for it. In this case, if you have this beam and it's resting on those neoprene pads, basically it's just that, resting. If it's just resting, it's only one reaction in this direction, and that's why you have a roller, which is the equivalent or the idealized version of the reality. Now this one here, if I get this part, I can lift it, and this is gonna have a rotation. And one of the things that you have to start getting around is that when I say rotation, it doesn't mean that it's gonna be like woo, rotating freely around the circle. No, it should be like that. But if you have a little rotation, that means that the moment is not restrained over there, and it's free to rotate. That means there's no moment reaction. However, I cannot push it because this bolt is preventing that sliding, and at the same time, if I get this, I cannot lift it because the pin is preventing it also with the nuts and the washer, meaning this is a pin for practical purposes. So today we're gonna do the same thing, but now we're gonna be working on 3D in the space, and we have plenty of we already went over this, I don't know why. Okay, but some examples. Look, the 2D, well, this is 3D actually, but you see this is a real support in a bridge, and basically depending on how this connection is here, it could be a roller or it could be a pin, that part, but I think it's a roller that is acting here. This is a pin, obviously, and you can see, and you don't need imagination because you can basically see here that is a pin completely. What about here? Well, here is a fixed support, obviously, in 3D. This part behave like a fixed support because you have the vertical reaction, the horizontal reaction, and these 2 bolts here separated by a distance basically are creating a couple, and that couple here is a moment, a resistive moment. However, whenever you cross, in this case, rebars like that, if I get this column and I try to move it side by side, what is happening there is that this point here is going to be able to rotate, and only you have a restriction in this direction and maybe a restriction in this other direction, but the rotation is free. So that behaves like a pin. And I'm sorry, I was explaining before, and I was saying here and here and here and here, and the mouse wasn't working. Now I see that the pointer is there again, so good. And this is like a rocker on the bridge, and this is a hinge. The difference between a hinge and a pin, this is a pin, it's a hinge. The difference between both of them, basically, I always define the hinge like an internal pin. A pin helps to support the structure with respect to the base, but a hinge supports one part of the structure with respect to the other part of the structure. But there are also 2 reactions, and that's it. 2 reactions and no moment reaction. 2 force reactions and no moment reaction, like the pin. We also covered determinacy, and we went over determinacy also, and we say when all the forces can be determined, all the reaction forces, using the equations, the static equations of equilibrium, then the structure is statically determinate. Otherwise, it's statically indeterminate. That doesn't mean that you're not able to calculate the structure, to calculate the forces. That means that in statics, if you're talking about 2D, you only have 3 equations of equilibrium, summation of forces, sigma x, y, and moment. And we assume the bodies are rigid, not deformable. But whenever you need the extra equation, you will learn that in mechanics of materials and future courses, and you start adding deformation equations and movement equations, rotation equations, and those are called compatibility equations. Now, how do you determine, how do you show if a body is determinate or indeterminate, if a structure is determinate or indeterminate? I say for every free body diagram, you have M bodies and R reactions. And what are bodies and reactions? And I will go over that in 2 minutes, 1 minute. Basically, if R equals 3 times N, you say that the structure is statically determinate. Otherwise, it's statically indeterminate. If it's bigger, the number of reactions is bigger than 3 times the number of bodies, it's statically indeterminate. And one thing that doesn't say here, but usually it's like that, if R is smaller than 3n, then the structure is unstable, and that's a different definition. Let me tell you what I meant by R and N. R, number of reactions. How many reactions here? 2. And here, 1. 2 plus 1, 3. 3 reactions. And how many bodies? From here to here, I think only 1 element. So I have 3 reactions and 1 body, meaning R equals 3 times N, meaning that is a statically determinate type of a structure. Now look at this one. This one here, this is fixed, this is a roller. 4 unknowns, 4 reactions, and 1 body. So R equals 4, N equals 1, meaning R is bigger than 3 times N. That's indeterminate. And because this is 4 and this is 3 times 1, 3, 4 minus 3 is 1, you say it's a statically indeterminate of first degree. Look at this one here. 3, 4, and I say the hinge is like an internal pin, right? So 2, 4, 6, 3, and 2, 5, and 1, 6. R equals 6, and then you have 2 bodies, 1 and 2, 2 bodies. And because 6 is equal to 3 times 2, that is statically determinate with this. It looks like a paradox because this one you can't, and then here you have 1 extra degree of freedom, 1 extra support, over there, internal support, and then you can solve it in statics. And this one you cannot solve it in statics. What about this one? So you have 3 reactions, 4, 5 reactions, 1 body, meaning 5 is bigger than 3 times 1. 5 minus 3, 2, statically indeterminate of second degree. This one here, well, this is when you have to start thinking how the support behaves, and this 2 doesn't have any problem, right? This is 2 plus 2, 4, but in the case of this, you have to start imagining. And if you make a cut, how do you make a cut here? Let me see, I don't see very well here. That's the way you should do it. You should get like a cut around this, something like that. But now you say, okay, let me work with this and let me see what happened here. If, sorry guys, I don't see anything here, and I don't see anything here. I don't want highlighter, I want my arrow. Okay, good. So you get this part only and you say, can I slide it in this direction? And the answer is yes, you can slide it. If you can slide it, there's no force reaction in that direction because it's free to move. What about if I get this part and I push it or pull it in this direction? Then you're not going to be able to do it because it's restrained. So you have a force reaction in that direction. Now the other thing is, what if I take this part and I try to rotate this in this direction or that direction? And you are not going to be able to do that also because when you try to move it in this way, this part is preventing the movement with a force like that, and this other part is also preventing the movement with a force like that. And those two forces together, what they are doing is basically they are forming a couple. And when they form the couple over there, you see that couple of forces here is generating that moment. So basically this support has 2 forces or 2 reactions, 1 force and 1 moment, and you have 2 here, 1, 2, these 2 and these 2 are the same, so 2 and 2 more here, so you have 2, 4, 6 and 2 bodies. So 6 equals 3 times 2. That means that this is statically determinate, and theoretically you should be able to calculate that. And I went to this example also. You can go on your own and check it. This is 2, 3, 5, 7, 9. 9 equals 3 times 3, determinate. And this one is 3, 6, 2, 2, 10, and 3 bodies. So this is statically indeterminate of first degree. What about this one? You have 3, 5, 7, 9. And 1, 2, 3 bodies, so 9 equals 3 times 3, that's statically determinate, and so on. Last case, hopefully, for statics, so you have 3, 6, 8, 10, and you have 1, 2, 2 bodies. So if you have 2 bodies and 10, 10 minus 3 times 2, 6, 10 minus 6, 4 degree, indeterminate. This is the same example that we saw before, basically. This is only one reaction in this direction because it can slide and it can rotate. So this is only one reaction in this direction, and then you will have 3, 4, 3, 6, 5, 7, 8, 9, and 1, 2, 3. That's statically determinate. Okay. Another thing that was covered is a two-force member, and this is just a really quick basic definition. A two-force member is, what it says is that whenever you have a member like that, if you neglect the self-weight of the member is not taken into account, is negligible. The only possibility that if you have a force here in this direction acting for this body to be in equilibrium is that the other force has to be acting in the same line. And this is called a two-force member. This is a very useful concept for solving some problems, and whenever we go to trusses, you're gonna see the meaning of that. Okay. Example of two-force members. Yes, that's what I was telling you. If you neglect the unit weight of these, for example, the self-weight of these, basically the only possibility for these to work is if you have one force and the other force in the same line. Same thing here. One force and one force in the same line, never in different lines or in different directions. And then I went through this and I said, okay, look at this thing. This is a really nice problem. You have to check it. You have to verify this problem. And I said the jib crane is supported by a pin at C. This is a pin here, and a rod AB. The load has a mass of 2,000 kilograms. So basically, you have to put there 2,000 kilograms multiplied by gravity acceleration to make it newtons. And it says neglect the self-weight of the beam, and what are the reactions at B and the reactions at C. Well, the way you do this is the same thing. You just do this, right? Cut it and cut it. When you do that, you have a reaction here and two reactions here, one X and one Y. Now, when you do summation, the way you're gonna solve this problem, and it's a group problem solving, I'm not gonna do it, but the way you're gonna solve this problem is you start by doing summation of moments here. Now, be very careful, because if you see this tension apply at this point, the tension applied, you see I was doing it again. The mouse, somehow the mouse stopped working. So, okay, now it's working again. You see this part here? This is a pin, and this is a tension. You're gonna cut this around like that, cut it around, and then you're gonna have two reactions here and one reaction here, one reaction in this cable, in this rod. And I was saying the easiest way to solve this problem is by doing moment at this point, at C. Whenever you do moment at C, the only unknown that you have left is the rod AB, a tension in this part here. But be very careful, because I know this tension is going to have two components, one vertical and one horizontal. The vertical component is going to produce a moment with respect to C, where it's going to be 4 times this component. How do I calculate this component? Well, I can calculate the angle. What is the angle? The angle will be, or the tangent of this angle will be, if this is 3.2 and this is 0.2, be very careful, because you have to say 3.2 minus 0.2, that will be this height, divided by this base, 4 meters, and that will give me the tangent of this angle. And if I do the inverse tangent, that's it. I can calculate the angle, which is basically a 3, 4, 5 triangle. Once I have that, I can say, okay, this one is gonna be this value, t multiplied by a sine of the angle, and this one is gonna be t cosine of the angle. Now the t sine of the angle, this one, multiplied by this distance, will give me a moment. But this is the part that you will have to be really careful. There is a homework problem that I assigned when this rope or this rod was at the center line and it was aligned with the pin. If that is the case, when this happens over there, of course the horizontal component is not producing moment. However, because there is a distance of 0.2 meters between the center line of the pin and wherever the tension is applied, the horizontal component is going to have this arm if I do moment with respect to C. So it's going to be the horizontal component T cosine of the angle multiplied by 0.2. That would be the moment. And then this force multiplied by this distance. And that's basically the way you solve that problem. So today we're going to be working with 3D equilibrium. And I used to spend some time here in this type of supports. It's the same thing, and I will, what is the difference between 3D and 2D, and the difference is 1D. So basically, what this implies for 3D equilibrium is that if you have an element like this is the rigid body. That rigid body is going to be able to move in this way, in this way, and in this way. So you have 3 possibilities for translation. But at the same time, it can rotate also in this way, or in this way. So you have 3 different rotations. The total number of equations is 6. Summation of forces in X, summation of forces in Y, summation of forces in Z, and summation of moments in X, Y, and Z, respectively. Now, if you take this support, you have to imagine how this moves, or how it doesn't move. The only possibility for this support to move, can you move it up and down? No. In this way? No. In the other way? No. Up and down? No. In this way? No. In this way? No. The only possibility for this to move is rotate about this point. Because even if I hold it like this and I try to rotate, it's not going to rotate. It's only going to go when I do this movement. So basically, the only free movement is a moment about that direction. So you have 5 reactions, 3 forces and 2 moments. Like, this is the camera sensor. Okay. What else? If a support prevents rotation of a body about an axis, the support exerts a couple moment about the axis, because it's rotation. Rotation is moment. And if a support prevents translation, then it will be a force. When doing 3D problem analysis, you have how many scalar equation of equilibrium? I already said it, 6 scalar equation of equilibrium. Application, well, once again, this is a ball and socket. Theoretically, this thing can rotate in any direction. This is like the old joysticks in the video games, in any direction. But you have 3 reactions, 3 force reactions restraining all the translation. But the 3 rotations are free, so that when you have that type of support produces 3 reactions. What about this one here? Well, this is a bearing. If you see this bearing here, same situation. Cannot move this, cannot move here. Theoretically, depending if it's a thrust bearing, it cannot move in that direction, in this direction, cannot move. But let's assume that it can slide. So you have 1 force and 2 force, and then you have 1 moment in this way and the other moment in this way. The only moment that is released is this one. So you have 2 forces and 2 moments for that bearing. Okay. Different type of supports. You have a smooth surface support. There you go. This is basically a roller. That's what it is. It's a roller in 2D or 3D. One force perpendicular to the surface. Ball and socket, I already discussed that. 3 force reactions and no moment reaction. Single journal bearing, same thing. One force, one moment, but it can slide in this direction or it can rotate in that direction. Then you have the single hinge. Single hinge, the only rotation that is permitted is in the direction of the hinge, like this. That means that the other two moments, this moment and this other moment, are restrained. And same thing with the forces. This is restrained, and that is restrained also. So the 3 forces are restrained and 2 moments are restrained. 5 reactions. That's what it produces over there. This is a very important note, especially when you are solving problems. You're gonna find a certain type of situations and problems that the statement of the problem is gonna claim something like 2 or more properly aligned bearings or hinges. If the statement of the problem says something about 2 or more properly aligned bearings or hinges, what this is telling you is that even though the bearing is able to have moment reactions, those moment reactions are not going to be needed because the bearings are aligned in a certain way that those are never going to be produced. For your purposes, what you have to do is, whenever you see this phrase or this sentence, you only are going to have forces generated, and your clue is going to be this. Basically, you have 1, 2, 3 supports here, right? Even if it doesn't tell you that they are properly aligned, if this is just a normal bearing not properly aligned, you're going to have 2 forces and 2 moments, 2 forces and 2 moments, and 2 forces and 2 moments. That means 12 unknowns. You're not going to be able to do that in statics. They have to be properly aligned for your practical purposes, I'm talking about, not in real life. So that's why you have 2, 4, 6, and then I can solve that in that way. When a body is in equilibrium, the net force and the net moment is 0. That means that you have either vector equations or you have 6 scalar equations of equilibrium. Okay, let's do this example. This example, it says you have the cable of the tower crane subject to a force of 840 Newton. A fixed support at the base A support the crane. Find the reactions at the base. Okay, I'm gonna use this one for solving it. This one. Good. This is the one that I'm gonna be using. So basically, this is the problem that we have. How do we solve this problem? Well, the problem basically stated that at the base here, okay, there you go, at the base there is fixed. If it's fixed at the base, then what you're going to have there is 6 reactions, 3 force reactions and 3 moment reactions. So you can do this in any way that you want to. Now be careful with this. You see, this orientation is really weird because this is the positive direction, and positive direction. Everything that rotates, well, let's start with the forces first. I'm gonna put the force here. I'm gonna have a force X, AX, a force Y, AY, and a force Z, AZ. And I'm pointing them in the positive direction. It doesn't mean that that's gonna be the final direction, because remember I explained before that whenever you do that, at the end, what is gonna tell you the direction is if the sign is positive or negative, your assumption was correct or not correct. Now the moment is assumed positive if it rotates in the direction of the axis coming out. Instead of using that notation for the little arrow curve for the moment, I'm going to do this. I'm gonna put a double tip arrow, which also represents moment, and I'm going to say this is moment AY, and here I'm going to have in this direction MAX, and in this direction MAZ in that way. Okay, what do we do? Well, summation of forces in X and summation of forces in Y. I have this force, and that force I have to convert it in Cartesian in the same way that we did before. So the first thing is convert that into Cartesian notation. How do you convert the force into Cartesian notation? Unit vector, position vector divided by the unit vector, and that's basically it. So I need the position vector BC, and the position vector BC basically is, if I'm going from this, you can use coordinates if you want to. Where are the coordinates of this point? Coordinates of this point are, in X is 3, in Y is 2, and in Z, no, not 0, in Z is 24. And this point here will be in X 15, in Y 10, and 0. And then because you're looking for this direction of the force, you subtract C minus B, and that will be 15 minus 3, 12, or 10 minus 2, 8, and 0 minus 24, negative 24. So basically this is going to be 12I plus AJ minus 24K. And that's what you have there. Now, the unit vector is BC. It's going to be the vector BC divided by the magnitude of the vector BC, the position vector. And if I want the force is going to be the unit vector BC, the force BC. It's going to be the unit vector of the force BC multiplied by the magnitude of the force BC, which is given. So if I want to find this, I can do it immediately and say the force in the direction BC is going to be equal to the position vector 12I plus 8J minus 24K divided by the magnitude of this 12 squared plus 8 squared plus 24 squared. Why don't you put it negative? I don't care if I put it negative because it's a square, so it's gonna be the same thing. Multiply all of these times the magnitude of the force, which is 840, and that will give you your value for the force in Cartesian notation. The force BC is 360I plus 240J minus 720K Newton. That's your force BC. For the first part of the problem, I already can calculate my summation of forces using equation of equilibrium, because summation of forces as a vector should be 0. What forces do I have acting here? The forces that I have acting are FAX plus AYJ plus ACK plus the force BC. And that's 0. Now I can say that from here I can use everything in I. AX plus 360 has to be 0, and AYJ plus 240, not J anymore, I don't need J, has to be 0, and AZK minus 720 has to be 0, which tells me the reaction in X is 360 positive Newton. I mean negative. Why means negative? What means this negative? That negative means that it's a little bit blurry. I don't know why. That's better, but it's still kind of blurry. Okay. So this negative, what it means in real life is that my AX was assumed in this direction, that the correct direction for AX was that. Now when I go here, AY equals negative 240 Newton. What that means is actually the same thing, that AY in real life, I assume it going in that direction, but because it's negative, it means that it's going in the other direction. And AZ is 720 Newton, and that means that it was corrected, assumed, and it goes up. And we already finished the easiest part, which is calculating the force reactions. Now, how do I calculate the moment? Well, I do summation of moments. Summation of moments with respect to what point? Well, you have any point, but I find easier if I use, I'm gonna change this here, and I'm gonna put the only moments here, only moments. I'm gonna say MAX, MAY, MAZ. I'm not gonna put the forces, just not to overcomplicate the problem, and because I'm going to do moment with respect to A. I'm gonna do summation moment with respect to A equals 0 as a vector. If I do that, the three forces AX, Y, and Z, AX, AY, and AZ are not going to produce moment with respect to that point, only the three moments for the fixed base, and then I have this distance here. What is that distance? Well, it depends, because remember, I can say it MAX plus MAY JI plus MAZK, the three moments, plus R cross F. Now that R, it could be several R's. You have to select the easiest one for you. Which one is the easiest one for you? Well, the easiest one for you will be, I don't know, for me, the one with more zeros, or the one that is more straightforward. Let's say that I decided to do this R. Is that possible? Yes. What is R? The distance from the point that I want to calculate the moment to the line of action of the force. That is a possibility. But this is also a possibility, and it's a better possibility in my opinion. RAZ is a valid R because it goes from the point to the line of action of the force, but one of the coordinates is 0, so why not to take advantage of that? So I'm gonna do this plus R cross F. Remember the cross product IJK, and R is gonna be from here to here, meaning 15 in X, 10 in Y, and 0 in K. And the value for the force, we did it before, and this is the force BC, 360, 240, negative 720. That's the value for the force, and that has to be equal 0. So basically, when you solve this system and you do the cross product, you're going to get MAXI plus MAYJ plus MAZK plus I that multiplies this times this minus this times that, but this is negative, so negative 7200 I, and then you say minus J that multiplies this times this minus this times that, but minus times minus is positive, so you have plus 15 times 720, and that's 10,800 J plus K that multiplies this times this minus that times that. This times this is 3600, and this times this is 3600. 3600 minus 3600 is 0, so you don't have anything else. That means that everything that goes in I goes together. MAX minus 7200 has to be 0. MAY plus 10800 is 0. And last but not least, MAZK, there's nothing, right? So 0. This value is 0. And now MAX is going to be 7200. What units are these? Oh, units. I forgot the units. Nobody moves. What are the units? R cross F. What are the units? Newton, meter, Newton meter. And MAY equals negative 10,800 Newton meter. Once again, what is the implication of this negative sign? The implication of that negative sign is that MAY, instead of rotating, coming out of the axis, the rotation will be in the axis. Not like this, but like that. That will be the implication. And this is a really easy problem to solve and to explain. There are many other problems, and if you go to my website, to my YouTube channel, you're gonna find several problems that are related to this, and you can go and watch them. Let me see what I have here extra. And I have another problem here, and this problem I'm not gonna solve it now in this video, but it's a nice problem. The way I approach this problem is now using the scalar approach instead of using just summation of moment here and do everything else. Now you start looking at the different axes and how it moves and how it rotates with the different axes. And you know, I'm just gonna put the slides 1 and 2 so you can see the slides and maybe copy them if you want to solve the problem, but I'm not gonna solve it for you. So you'll see the results and try to solve it on your own. And if you have any question, well, at least my students here, you know where I am. Whereas here, the rod AB is supported using 2 cables at B and a ball and socket at A. Ball and socket, 2 cables here and here. How many unknown support reactions exist in this problem? Well, this is not a pulley, so this is one reaction and this is one reaction, 2 force reactions, right? And what about the ball and socket? Ball and socket has 3 force reactions. Basically you have 5 force reactions. There's no moment reaction. The only way that you could have a moment reaction is if any of the supports have a moment. What else is here? In additional couple moment in the vertical is applied at AB. An additional couple moment in the vertical direction is applied at the rod AB at the point C. Where is the point C? Oh, where's the point C? C, here. Okay. A moment. And what happened to the rod? Well, the rod is gonna try to rotate like that, in that way, but probably these two are gonna keep it restricted in position. Oh, nicey. Look at that. Group problem solving. Guys, copy. Remember what it says here? Rod is properly aligned. If it's properly aligned, means these bearings are only producing 2 forces and no moment. This is a really nice problem. I think I assigned it as a homework problem also, so try to go over it. I'm gonna make this channel available, this video available in the YouTube channel also, so you can go and watch the results. Okay, that's it, because right now I have to run and teach my real class. See you later, guys. Have a good day. See you later, alligator.